1,000. That's what p hat was. That was you had 101 people get sick out of 1,000. What's little p for your assumed population? You got it, Alina. Look up at your null hypothesis. It's whatever value is in that null hypothesis. It's 12%. Right? It's 12%. So this guy right here, I'm going to go one more step here. We're going to come back and focus bottom in a second. So this is 0.101 minus 12% minus 0.12. Which ends up being how much of a difference? 1.9? Check me on this.
Yeah.
Negative, right? So it's negative 0.19. Okay, great. Negative 0.19. As you can see that whole string of arithmetic there. Okay, we're good so far. So that means it's down how much? 1.9% from the assumed 12%. But say that again.
Yeah.
Right?
Okay.
And it's down because it's negative. So yay, our vaccine's working.
Yeah.
Maybe. Why? It appears right now, but what haven't we accounted for? There's a margin of error around that 1.9%, correct? If I gave this to 1,000 more people, am I going to get 101 get sick again?
No.
Am I going to get close to 101 get sick again? Unless this was outlier data, yeah. But the question is, we have to allow for all of that in this one sample. So that's where this guy comes from down here. This guy takes care of how unusual that value actually was. So this is going to be your standard error. Now this is going to look a little weird, and you've probably forgotten this already, and that's totally fine. This you were trying to, well, sorry. Your standard error looks like that. That's your inferential standard error for a binomial random variable, which this is. This is binomial. Either you have the flu or you don't have the flu. It's binomial. That was the adjustment we had to make. If you remember, you're probably trying to forget. Like I said, you're probably trying to forget this. But that's the computation we have to make for the standard error of this bad boy. So we just got to plug and chug a little bit. P is 12%. Remember what Q is? Good. The rest. Great answer, Jane. That's exactly right. The rest of it. The other 88% chance of failure, which in this case is actually not getting sick. This is one of those weird cases where success is getting the flu, which means failure is not getting the flu. But why do we call it success? Because we're testing that. We're trying to see the presence or absence of the flu. Success would be getting the flu. All right, and then divided by the 1,000, it gives us a nice indicator that as we sample more, our curves get higher and tighter. That's going to go down. So we end up with 0.12 times 0.88 divided by 1,000. I get 0.0001-ish. You got, square root, excuse me. So 0.01-ish. Let me get a little more precision than that. Whoops. Square root answer. 0.01-ish, yeah. I'll do this. Please, Spence.
Is it supposed to be 12% times 88%?
Versus what?
Versus 10 times 90-ish?
Why 10 times 90? Oh, 10 because of this 10 right here.
Yes.
I love that, Spencer. You already hear that question? This is a fantastic question. Spencer asked a very, very good one. He's remembering back to single portion confidence intervals. And the standard error for those bad boys was built around p hat and q hat. No, this is a great question, Spencer. Thank you for this. He's saying, why isn't this p hat and q hat? Why is it p and q? What curve are we on right now?
The population.
We're on the null population curve. So we're making the assumption that our data lives on that curve, Spencer, and we're trying to prove that it shouldn't be on that curve. That's why we're using P and Q. I love that question, by the way. Thank you. It's a fantastic question. We're trying to show if the vaccine works that our data should not be on that curve. But we're going to build the curve around that 12% to show that it doesn't. Or maybe it does. We're going to see one way or the other if it does or doesn't. Fantastic question, man. Fantastic question. Good. So essentially, what we have now is we have this right here. And let me get some precision going over here. I've got negative 0.019 divided by, let me just do this all at once here, square root of 0.12 times 0.88 divided by 1,000. I end up, oops, hang on a second, did something wrong, I didn't group correctly. Stupid. This is why I can't stand doing these things manually. Just divided by square root, there we go, 0.12, 0.88 divided by 1,000. There we go. I get negative 1.85. Well, here's the mess that I just had to, sorry, that's the mess I just had to calculate.
That's not
What's the matter? So there's your p hat minus your p. Here's your standard error. The important thing is this guy.
yeah.
It's z is about equal to negative 1.85.
Oh.
Negative 1.85 what? This is z-score. So what are z-scores again?
Standard deviations.
Standard deviations. Let's take 5. Yes, let's take 5 because I'm really seeing the glaze now. Let's take 5 and come back and see what the hell that means. It's on the curve. Say that again?
Are we ever going to do this like this?
No, God, no. Once. Once. Carrie, please.
Well, I said, no, I'm good.